Started with our material for today. Um, so let's go ahead and begin. We're finishing up with improper integrals for Unit 3 material. Keep in mind that today you're going to have 3 videos to watch. You're going to have this video, and then a worksheet video, and then a video of us going over the Unit 3 review. So let's get started. Improper integrals. So first, the fundamental theorem of calculus states that this integration is defined as here. Now, this integration only applies to integrals of a finite interval, a to b, where a and b are numbers. An improper integral is one where the limits of integrations are infinite, like what you see here. Can these all be done? Yes, but not necessarily with FTC just yet, the fundamental theorem of calculus. We cannot apply fundamental theorem of calculus to these because infinity is not a number. So we need to take the limit of proper integrals. So recall some basic limits. The limit as x goes to infinity is an infinity. The limit as arctangent as x goes to infinity is pi over 2. The limit of 1 over x as x goes to infinity is 0. The limit as 1 over x to the power of p, where p is a positive number, goes towards 0. The limit of ln of x as x goes towards infinity is infinity. The limit of e to the x as x goes towards infinity is infinity. The limit of the square root of x as x goes towards infinity is infinity. The limit of 1 over e to the x as x goes towards infinity, that's not that obvious. I'm going to rewrite it like this, which lets me rewrite it as the limit of x goes towards negative infinity of e to the x. So just e to the x going towards the left is going to be 0. Okay. So we have all these limits here, and hopefully these will come to us as we continue to do this. Now, technically speaking, we can do limits of infinity, but just not right away. Infinity is not a number. We can't just plug in f of infinity. In order to do this, we replace the infinity with the limit. So we have infinity here. We write as limit of t goes to infinity, where t replaces that infinity. Same thing with negative infinity. If we have this, then we replace it with the t, and we say limit as t goes towards negative infinity, where the limit is implying to the result of this whole integral. So the limit does not get to sneak into the integral until we have fully evaluated this integral. When the limit exists, the integral converges. We get a real number for the solution. If the limit does not exist, the integral diverges, and we get does not exist or a plus or minus infinity. So let's start here. We have an infinity. So before we even evaluate this, which is a very simple integral, we replace it with t, and we say the limit as t goes towards infinity. Then from here, you can just do actually, I'm going to go ahead and go step by step. E to negative 2, add 1, or dx, add 1, so that's going to be negative 1. So that can be written as the following. X to the power of negative 1 over negative 1, t 1. That can be further simplified. The negative will escape. And then we have 1 over x, t to 1. Then we plug in the values. We get negative the limit as t goes towards infinity of 1 over t minus 1 over 1, which we can just simplify this to be 1. And then you can go ahead and apply the limit here. We know the limit of a constant is just the constant, so really what we're doing, and I'm going to go ahead and let the negative occur here. We have negative limit as t goes towards infinity of 1 over t, and then plus 1. And then from here, we know that this limit should go towards 0, and we just have an answer of 1. So the answer is 1. And then we can say that the integral converges. because the limits are exist of this setup right here. Okay, I'm just checking my answers key in case I'm missing anything. I do not think so. No. Okay, let's move on. Number two. So number two states following. So we have the integral from negative infinity to 0, so we need to make that be a t. Limit as t goes towards a negative infinity of t 0, 1 over square root of 3 minus x. Dx for here, we should do a substitution, so that's what I'm gonna do. Let's try to write over here. It's because I have white out there. U be 2 not 2 3 minus x. Du then is negative dx, and then that means that negative du is dx. Wait, that kind of got blurred because of the whiteout. That means that negative dx is du, sorry, is dx. Okay. All right. Then from here, we can go ahead and do that u substitution. A negative escapes all the way to the front again. T0 of 1 over the square root of u du. I'm going to rewrite that as a power just to make sure I don't mess anything up. U to the power negative 1/2 du. And then that's going to be you're adding 1 to it, so it's just going to be square root of u, or u to 1/2 over 1/2. From 0 to t. I'm going to let that escape. So it'll be a negative 2 times the limit as t goes towards infinity of the square root of u from 0 to t. And then I'm going to plug in back u. Hi, sorry. I keep forgetting to look at the camera. Negative 2 limit t goes towards negative infinity of, well, I forgot the negative here. Square root of 3 minus x. And then from 0 to t, and then I'm going to plug in 0 and t respectively. Negative 2, limit t goes towards negative infinity of square root of 3 minus square root of 3 minus t. Okay, all right. Evaluating the limit here, I should get just a square root of 3, and then distributing limit evaluating here, I should get a negative, and then because we're going towards negative infinity, that means negative t will be going towards infinity, and that means this value will be ever increasing under a square root, which means it'll go towards infinity. Which, because of the minus infinity, will be a negative infinity that will be going towards. But at the end of the day, we have the technical issue. Even after, I mean, yeah, you can distribute this if you want, but you could stop here. What was it, 2 over 3, and then 2 times infinity is still infinity? You could stop here because at this point we have an infinity. And while this is a bona fide number, this is definitely not. So the limit diverges. I mean, the integral diverges because the limit does not exist. All right. Let's up the ante and let's go ahead and say that they're both infinities. So for improper integral over both infinities, we are going to use the property where we can split them up. Now, typically, when we split them up with some variable in beside, we pick 0. However, there is now this technicality. If both integrals converge, the initial integral converges to the sum of those individual integrals, meaning that if this guy is good and this guy is good, those limits exist, then that whole thing has a bona fide answer. However, if one or both of these integrals diverges, then the whole thing is divergent, and that limit does not exist for the whole thing. Okay, so let's go ahead and figure this out. Now, before I even touch this, I see that both of those expressions are the same. So I'm going to take advantage of that, and on the side, just figure out that bare minimum antiderivative of x e to the x dx. This is not easy to do. There's no like derivative of something appears as a multiplicative product. I'm just going to do not use substitution, integration by parts. So remember, we want u, or here, I need to do a different color now. We want u to be something that gets smaller. So du is just dx. And then we want dv to have a very palatable integration. So e to the x dx. So we know that that is just going to be e to the x. So multiply those two, we get x times e to the x minus the integral of this, e to the x dx, which is just e to the x. And then plus c, technically, right? But because we're about to plug it in here, we don't have to worry about this plus c, so this is part of our answer. Now, we need to go ahead and let this sort of be what we use for this guy. For this, I want to color code just a little bit as well because I want to make sure that we know the difference between these two notations. So this limit, I'm going to rewrite it here. Here, I should choose a different color since I'm now back to the original problem. Negative infinity to infinity of x e to the x dx got split up, right? Negative infinity, 0, x e to the x dx plus 0, infinity, x e to the x dx. Now, this both will get replaced by t. So you could either have two options. You can either use another letter, one that you won't get confused with, or just do some visual, these are two different t's. Because we have done the thing in the past, or okay, maybe not we, I'm getting confused for my Cal 1 class, but sometimes you start off with two different limits and then you end up recombining them. So we want to make sure that the two t's are separate so we can't even fall because first they have to be the same limit on the bottom and they're not going to be. But we still want to fall for that trick at all. So we want to make sure in any sort of capacity. So I want to make sure that we differentiate that. So the limit of t goes towards negative infinity of this integral t0 x e to the x dx, and then plus the limit as t goes towards infinity from 0 to t of x e to the x dx. But I'm going to color code these t's. Let's make this one was color. I think it's going to be like a pink. No, it's a red. Okay, let's make this the red t. And we'll make this the green t. All right. We already know the integration of this. We did it over here, so I'm just going to copy and paste that. The limit as t goes towards negative infinity of this bound, we have x e to the x minus e to the x from 0 to t plus the limit as t goes towards infinity, of x e to the x minus e to the x from t to 0. And again, that's red, and this is green. So we're gonna go ahead and I think I'm gonna do it over here on the bottom. Plug those in. We get 0 on this first guy, and then we get here 0 minus e to the 0, which is just 1, and then minus, I'm gonna do a full brackets over here, minus t e to the t minus e to the t. That's gonna be all of this. Oh, I forgot to write that in the first part. All of this with the limit as that t goes towards negative infinity. And then plus a similar thing for the limit as that goes towards infinity of e minus e. I'm going to add the t's right now, then minus 0 minus 1 for the green t's. Okay. So for here, we technically don't have it. Well, we know the answer for this one, and we can figure out the answer for this one a little bit, but I rather us visually show the answer. We know the limit of these guys are just gonna, be whatever, or be the constants. But for here, we can do a trick where we take out the t to be t minus 1 times e to the t. T minus 1 e to the t, where we just take out the e to the t, respectively. Now, we have a beneficial thing over here. The beneficial thing over here is that if we have t going towards negative infinity, and we have t going towards negative infinity, then this will be 0. So, and then this, because there's a t minus 1 is still going towards negative infinity, we'll have, in sort of a layman's terms, negative infinity times 0, which will still come out to 0. And then over here, we have infinity times infinity. And we have an infinity times infinity, which, positive numbers will still go towards infinity. So you can either, at this point, call this to play or call this to play. But you can almost just stop midway and be like, well, there's no point going any further. That limit is not going to converge. That limit is also not going to converge. So therefore, this whole integral, and this limit's not going to exist, this limit's not going to exist, excuse me. So then the whole thing is a wash. You could either point one of these out. If this was like a test question, I would want you to point maybe verbiage of like limit does not exist here. Or you could say that for here as well. Or actually, no, for this it exists. It's 0. I don't know why I said that. Let me just double check that here. I'm going to check that visually. Although I'm not going to make a question on the test where you have to use a graphing calculator. I typically want to stray away from graphing calculators just because, in my opinion, you really don't need them. Yeah, it's going to be 0. Okay, I had a feeling. Okay. Then, this limit does not exist here. Oh, so really you would just point out this. But either way, you would, if there was a multiple pieces, you just point out the one piece that doesn't exist, and you can just literally stop there and be like, this, I think, did it skip the next page? No. This diverges, and that would be your answer. So just keep that in mind um, as you do the homework and the review for this. Okay, last one. And this is a special case. It's a discontinuous integrals. Now, if f of x is not continuous at some point in the interval a to b, then this integration a to b f of x dx is called an improper integral with a discontinuous integrand. So then you have those boundaries listed in the following. If f of x does not exist or is not continuous at a, then you technically are forced to write it as a limit. Now, actually, wait, let me finish this part over here, and then I'm explaining why the plus, why the minus. If f of x does not exist or continuous at b, the ending point, then you're going to go ahead and use this limit to denote that as well. Now, y plus and y minus. Well, don't forget, plus means you're coming from the right. Minus means you're coming from the left. If you're doing some kind of integral bounded on a to b, and you need the best approximation possible, but a doesn't exist, well, you know you can go all the way up to a, very close to a. However, we don't care about the limit as it approaches a. We more specifically care about the limit as it approaches a from the right. Similarly for b, if we want to get to b but not all the way close to b, and we can't do exactly b, then we must approach b. But if it's from this value a to b, then we have to approach b from the left. So that's why it's left and right respectively here. So again, this number line logic is showing why we have to say from the left and from the right. Now here we have the following, the integral from 0 to 4 of this function. Now here, we're not told anything else, but visually, we should see that one of these guys does not work, and it's 4. 4 does not work as an entry point here, because we know that 4 minus 4 is 0, and the square root of 0 is 0, that's not the bad part, but we're dividing by 0. So we know that's the issue. So we must rewrite this as the limit as t goes towards 4, and it's the top part, so from the left of this integral t to 0, 1 over the square root of 4 minus x dx. From here, let's do a u substitution. D is equal to negative dx, and then negative du is equal to dx. The negative will escape all the way outside the limit. Oh, sorry. From 0 to t of 1 over square root of u du. And then I'm just going to copy and paste the result we got earlier, sort of with this, where it's a positive because the negative will slip out. Limit as t goes to 4 from the left of 2. Here the 2 escapes square root of u. Okay, let me see, I'm just double checking everything. Um, Wait, I don't think a negative escapes here. No, no, negative doesn't escape. My bad. So it is just -2. Let me double check. We literally did this problem right here. Yes, and I don't know why I thought another negative appeared. Okay. Then we plug in back this u, which is different. Which is the square root of 4 minus x from t to 0. And then you go ahead and plug in those values. You have -2. Limit as t goes to 4 from the left of square root of 4 minus t, and then minus the square root of 4. Okay, well, if we apply this limit because it's going to 4, and we're allowed, 4, we can just use substitution basically for this, then that's just going to be 0. And then the limit of a constant is the constant, but I'm going to simplify that to square root. So we have -2 times 0 minus 2, which comes out to 4. 4 is my final answer, and this integral does indeed converge. Okay. Let me just check if I didn't miss anything. I did not, and that would be my answer. All right. So that's going to wrap up the Unit 3 material. I'll see you in a bit for the worksheet, and then afterwards, the Unit 3 review video. Let me know if you guys have any questions. I'll see you next one. Bye-bye.